Today, we're diving into the very engine of how we reason. We're talking about logic. But we're not just going to look at the dusty old rules. We're going to uncover a really powerful modern upgrade. Something that lets logicians do what sounds kind of impossible. Turn logic back on itself to analyze its own rulebook from the inside. So let's just start with a huge question. What if the fundamental rules we use to build arguments weren't actually set in stone? What if logic was less like a fixed toolkit and more like an evolving system that we can actually improve and analyze as we go? That's the core idea we're unpacking here. Now, to really get the upgrade, we've got to look at the standard operating system for reasoning, which is called natural deduction. Just think of it as the basic set of tools the logician has. You've got a handful of fixed, super reliable rules, like that classic, if A is true and A implies B, then B must be true. You use those to build proofs. It's powerful, for sure, but the rules themselves, well, they're just tools you can't really change or question from inside the system.
But this is where our story really kicks off. Because that standard toolkit, as good as it is for proving things, it has its limits, especially when we want to turn the lens of logic back onto itself.
And this brings up a really critical point. What happens when we want to reason about the rules themselves, right? How do you ask if a rule is well designed or how it connects to another rule? The standard system doesn't really have an answer for that. Its tools are built for working with formulas, not for analyzing the tools themselves. So that very limitation, it sparked a truly brilliant innovation. Logicians came up with a way to expand what logic could do, which brings us to our first major breakthrough. The calculus of higher-level rules. Let me put it this way. In standard logic, you're basically a chess player. You're following the established rules of the game, period. But in higher-level logic, you get to be the game designer. You can temporarily add a new rule, treat it like an assumption, and just see what happens. You can test it, play with it, and then draw conclusions about the rule itself. It's a huge shift in perspective.
So, how does this actually work? Well, it's basically a three-step dance. First, you temporarily assume an inference rule exists, just like you'd assume a formula is true in a normal proof. Second, you use that new rule to derive some kind of result. But then, and this is the magic part, you do the third step. You discharge that assumption. And that lets you form a conclusion about the rule, saying something like, okay, if this rule were valid, then this other thing would have to be true.
So why is this such a big deal? It lets logicians analyze something called proof-theoretic harmony. Now, that's a fancy term, but it's basically the idea that a logical system should be balanced. For example, the rules for introducing a concept like and should be in perfect sync with the rules for using it. This new calculus lets us test that balance from inside the logic itself, making sure the whole system is well designed and doesn't contradict itself.
Okay, so treating rules as assumptions, that's one way to upgrade logic, but it's not the only way. There's another approach that's less about deep analysis and more about formal elegance and, well, standardization. And this brings us to the quest for a universal format for rules.
This second path is known as general elimination rules, or GERs. The goal here is just pure formal elegance. Instead of having tons of differently shaped rules for every logical operator, the idea is to create one single, standard format that all the so-called elimination rules can fit into. It just makes the whole system cleaner, way more consistent, and a lot easier to work with. So you can see we've got two pretty different philosophies here. The calculus of higher-level rules totally changes the game by letting rules become assumptions. Its goal is a deeper, almost philosophical analysis of logic. General elimination rules, on the other hand, kind of keep the game the same, but they redesign all the pieces to be uniform. Their goal is all about efficiency and elegance. Okay, so we've got these two big theoretical upgrades, but what can we actually do with them? I mean, this isn't just an abstract exercise. These generalized rules unlock some incredible new powers. And honestly, the applications are seriously impressive. This upgraded logic can automatically generate rules for any logical operator you can think of. It can create these powerful general rules for quantifiers like all and sum. It can even take axioms from a mathematical theory, like, say, geometry, and just turn them directly into formal inference rules, plugging them right into the system. It's amazing. And here's a really concrete benefit. Get this. One of these extensions, called contextual deduction, actually leads to shorter, more efficient proofs. This creates what's called an asymptotic quadratic speedup. In simple terms, that means that as your proofs get more and more complex, the time you save doesn't just add up, it multiplies. It is a massive performance upgrade for the act of reasoning itself. Okay, so we've seen how logic can get this major upgrade and what that new power can do. But let's zoom out for a second and ask the big question. Why does any of this really matter? What's the ultimate takeaway?
When you boil it all down, what this really means is that these higher-level and generalized rules provide the essential machinery for modern proof theory. They make logic more flexible, more expressive, and way more powerful. They allow the very framework of reason to adapt to a huge variety of contexts, from computer science to philosophy to math. This is what keeps logic a living, evolving field.
And that leaves us with a final, pretty wild thought. We tend to think of systems like logic or math or even law as these fixed, unchangeable things. But as we've just seen, even the most fundamental rules of reasoning can be examined, generalized, and improved. It really makes you wonder, if we can upgrade logic, what other foundational systems in our world are just waiting for their own revolutionary rewrite?